Worthwhile starting with these two quotes you saw briefly, but Stuart Brand says information wants to be free and expensive. And then another favorite quote from Einstein is a theory is something nobody believes except the person who made it, but an experiment is something everybody believes except the person who made it. Of course, we believe our experiments, but we know where the uncertainties are. We know that there's parametric uncertainty, there's systematic uncertainties, and we have to capture that. Furthermore, we know that it's wonderful when your model goes right through the data points, but they still may not be in agreement because there may be systematic errors in each one. So when we work with both modeling and theory and with experimental data, we know that we have to balance. We know that there are uncertainties in both. So my focus is going to be on the larger idea of an international data cyber infrastructure, and I was asked in particular to talk about the things that were going on in the United States right now, but with an eye on the world, and through the Combustion Institute, which is indeed international, and other related international initiatives that have been going on in this area, where the goal, again, an international data cyber infrastructure, in particular, from our concern for combustion science and technology, which at one level means application and codes, but actually more than that. It really means that there is a multi-part aspect. There's software that's involved. There's hardware that's involved. Even if it is in the cloud, you have the computer that you're working from and the server that you're working on. In addition, people. People are very important for support and the culture of sharing data. I have a close colleague on my apparatus at Lawrence Berkeley Lab, Katarina Kose-Hunghaus, who's president of the Combustion Institute. She's very concerned about sharing raw data because other people will not analyze it correctly, she fears. Well, that means that we have to understand the calibration factors, the methods of data collection, the methods of data analysis, the whole problem. And it is there are art parts as well. So I want to start off talking about the activities that have gone on, over the last 30 or 40 years that still hasn't taken it. But if you go even further back in the US, the JANF tables, many of you have used, the Gordon and McBride advances, Sang and Hampson's database, now online, the NIST webbook, CMCS, and a 2005 U.S. National Science Foundation activity that gave rise to Rushik's active thermochemical tables, to reaction mechanism generator, and to PRIME, and then to an important U.S. National Academy study involving computer science and combustion people, to a study that was sponsored by NSF on data cyber infrastructure, and finally to the activities that have gone on in the Combustion Institute and other initiatives. So what our conclusion is among this has been to build on PRIME, but that is like saying we will have a language that we'll agree on in common, but we have our own languages too. So there needs to be enough unity but enough diversity to accommodate different needs. So let me very quickly skip through those first topics. JANF, the Joint Army, Navy, Air Force analysis, was developed in part because of the need to understand rockets, rocket exhaust, and calculate exhaust in equilibrium. But it required coming up with better thermochemistry. It was one of the first reviews of data that used computers, although it was using computers largely to take molecular parameters, print out thermochemistry in organized fashion. Furthermore, though, for this rocketry issues, of course, computers had originally been developed to look at ballistic trajectories of, say, artillery shells or then ballistic missiles. Well, that's not very combustion-oriented except for the propulsion. For the propulsion, you really need to have functions. So Sanford Gordon and Bonnie McBride, working with the NASA U.S. Lewis Glenn Research Center, had developed a code for free energy minimization to look at equilibrium compositions that were produced. And of course, they needed the functions. So Bonnie developed the so-called NASA format that many of us are very familiar with, a polynomial heat capacity with the enthalpy and entropy and free energies that result from that. Then as we moved in the late 70s and 1980s into mechanistic modeling, Jim Miller, Bob Key, Jürgen Varnetz, Charlie Westbrook, Fred Dry, and others were developing both the mechanisms. There had begun to be enough critical mass of elementary reactions that were understood parametrically, or at least we thought we understood them well enough parametrically, that we could go ahead and do detailed kinetic models. That led to ChemChen at Sandia, and more recently to Cantera and to Sarathi's Cloud Flame. But Wing Sang was one of several people who was doing analyses. He said, let's consider all possible reactions. Many of us have used the Sang and Hampson, other Sang papers, and the NIST Kinetics database. Of course, there was Balch, the CODATA effort. There are many efforts around the world. But the idea of trying to review everything as individuals, take the data and say, which is the best number, what is the best average, trying to do an analysis there. But of course then came Tim Berners-Lee and the World Wide Web at CERN, spilling out around the world and becoming truly a World Wide Web. So the NIST Chemistry Web Book, which again many of us use, is a wonderful infrastructure of data. If I need ionization energies, if I need thermochemistry, if I even remember what's the name of that molecule, pop to the NIST Web Book to find that. Very useful tool, and a signature of things to come, I think. So I want to get to some specific, more recent examples. In particular, first, in 2001, the United States Department of Energy funded a project called CMCS, a Collaboratory for Multiscale Chemical Science. It included diverse areas from quantum chemistry and thermo to kinetics, mechanisms, reactive flow modeling. The project ended up being focused more on computer science because the challenges of handling the diverse data that we work with was so challenging. Again, from long-running detailed quantum chemistry calculations to complex reacting flows, laminar and turbulent reacting flows. But there were three pieces of code and data analysis that came out that are useful for us that have been very significant. The first, I'd mentioned Branko Rusic's active thermochemical tables. You can go to on the web, but it uses this approach that Ned was describing of the network of data, how the thermochemical parameters, enthalpies in particular, are derived from a network of different pieces of information, and looking at the uncertainties to say what is the tightest uncertainty. I have sat on the IUPAC panel for reviewing thermochemistry of radicals, and we found that Branko's method, in some cases, even for radicals, you could find that all the best predictions were hitting in this tight range of combined data analysis. The prime method that you heard about yesterday, that many of you are familiar with anyway, also came out of this. And then National Science Foundation ran a cyber-enabled chemistry program. Celeste Rolfing, a longtime member of the combustion community as well at Sandia. Two things. One was the idea of RMG, Bill Green, and now Richard West at MIT and Northeastern, respectively, doing automatic generation, very similar to the sort of approach that Bastien Leclerc and her group have worked on with X-gas at Nancy. But this idea of generating mechanisms, not necessarily to say it's better, but to make sure that when we generate mechanisms, do we forget things? Yes. So The cyber-enabled chemistry also funded the continued development of PRIME and the notion that the two would be combined together. Again, a US-focused approach, but not with an idea of being restricted to the US, and not even restricted to the idea of being an absolute truth. It's to be a contribution that would work with others, but the idea of having a data depository and data library, in other words, the initial deposition of data that you have, whether it's parametric data or experimental data from, say, a flame or the like, and also the testing of it. You'll hear more about that in Nadja Slavinskaya's talk this afternoon. But there was another factor that entered in the United States that may be more distinctive. Our legislature, the Congress, now requires agencies to get data management plans from any awardee. Now, in 2006 to 2009, I was working at the National Science Foundation, and I wrote the original draft for what NSF's requirements are. But fortunately, the definition of data that was recorded, which is fairly general, really means analyzed data and the metadata that go with it. It's not necessarily saying you have to report every millivoltage of every thermocouple, every analysis of heat lag through a thermal well, whatever. It's really the sort of data that would be published, but in digital form. And I don't mean a digital graph, but the points that are on a graph, because many of us have spent too many hours digitizing graphs so that we can test our models against them. Interestingly, they did not require preliminary analyses or raw data. So that's how the US plan is. But it requires that there be a plan for how data will be shared. The philosophy really was if it's publicly funded, it should be publicly shared with certain restrictions. So while I was at National Science Foundation, we formed a coordinating committee for combustion research, MACR. And early on, we identified combustion data cyber infrastructure as a very important part of what we needed to work on. So the US combustion community reviewed, and that PRIME was the only option. The thought was, let's support that. But it's been a long path. It's not necessarily easy to use. People don't necessarily want to share their data. So there are challenges there. So as a result, the coordinating committee, MACR, pooled funds from different agencies to fund a study run by Mitch Smook, but involving many prominent members of our combustion community, but also from the data science and computer science communities. The download, I think the address is even on the, we may have put it on the program, but really just look for Transforming Combustion Cyber Infrastructure and bam, it will pop up. It's a very interesting read. It's a little bit grand in its view. The idea of a unified combustion cyber infrastructure, movement of data, sharing of software tools, and they said 5 years, 75 people years. And the word was quickly, you must be kidding. That kind of money is just not available, especially with the uncertainty about whether the community actually wanted to share data. A number of journals signed on. International Journal of Chemical Kinetics had said, no, we want to have a data cyber infrastructure so that data are stored on that we can make use of. So there was obviously some interest. So in response, the National Science Foundation sponsored a workshop with the idea of if you can't spend big and start fresh, because that was the thesis of the study that was run. Assume we know nothing, let's start all over again and say, well, can we build on things that we have right now? So we met 5 years ago, 4 or 5 years ago at North Carolina State and concluded that building on the PRIME foundation made the most sense because it was the most developed platform that was there. It was also clear that it had to be structured differently, not just in a computer science sense, but in terms of community involvement and management. One person, Michael Franklak, had been carrying the load pretty much and catching the complaints as well, but there was the sense that there needed to be a broader base of management, which has now actually happened. So, but there were technical challenges, version stability, the learning curve to use it, which said, well, you must have, and indeed there's video training now, and work on development of online or in-person. But again, as I said, the operational, cultural challenges, not only community management, community buy-in, and this culture. There's a business saying that largely has to do with business mergers and acquisitions that culture beats strategy every time. That is, you can have great plans, but you really have to have a culture of data sharing before this works at all. So instead, again, this $75 million plan was not possible. We tried to come up with a minimal effort. Again, it was funded by US funds. It cries out for international funding, but again, there was a sense of taking a step. Nevertheless, even this, the agencies decided, no, until the community wants it, we won't take the step. So at the last Combustion Symposium, we all saw a lot of interest from the community in different ways. There was, before the symposium, the International Flame Chemistry Workshop, there was a large group discussion that I see several people who were at that discussion who were considering what data must we have, how can it be shared, what formats should we have. Somewhat similar to this, it was a flame chemistry workshop, but there's the realization that that extends to many types of different combustion systems, to furnaces, to reacting turbulent flows, to laser diagnostics, all sorts of data. So there were action item commitments, and I'll tell you how those turned out, but also the Combustion Institute board had discussions on whether the Institute should sponsor planning of data cyber infrastructure. There was a pot of money that the Combustion Institute wanted to invest in new ideas. So as it turned out, I'll tell you, Jackie Chen led a task force proposing a way to do that. And then there were several papers. Alice and Gigran aren't here, but Thomas and I are here. Several papers focusing on data science, including this major effort that Thomas and his group did looking at hydrogen-oxygen data set and classical optimization of parameters that were there, finding a number of parameters that could be improved by doing that. So after the symposium, there were several responses. One was from the government agencies. They said, again, not necessarily by themselves, but that we will invest real money if an institution, presumably the Combustion Institute, takes responsibility for a continuing lifetime, because a 5-year plan is not enough. We have to be talking about something that in one evolutionary form or another goes on into the future the way books have lasted, our original virtual learning environment books, the way journals, and so on. So somebody has to take that. Jackie Chen, again, I mentioned the task force. They proposed a modest 2-year planning initiative, the idea of taking a board-led Combustion Institute Cyber Infrastructure, CI committee, with a small group of members to develop and coordinate the strategy, not by themselves, but representing the community. A portal page on the Institute website that would have links to pertinent data pages, to data cyber infrastructures that exist, and to new community data sites as they develop. And finally, community buildings, seed grants. So such as the CFD community, such as the turbulent non-premix community that is already quite developed. So let's give them some money to define formats that are needed for those types of computations, those types of experiments. Well, the decision was to fund some new awards instead. So that avenue has not worked out, but I'm sure it will continue to be revisited. There was a large number of board members who were very interested in taking initiative on this. So in parallel, there were grassroots responses. I mentioned the flame chemistry workshop. There was a statement that was worked out. There were 37 people who were co-signatories who all agreed with this statement that is on the web on what could be done, what sort of formats were needed, what sort of data were needed, what sort of questions had to be addressed. In general, it articulated a vision, guiding principles, and these three goals: identifying the software and format needs, that's very much the topic we're focused on here today, disseminating those needs and the format, and reaching community agreement. The 37 participants didn't say that's everything, but they agreed that the statement was a good representation of what should be done. And then implementing steps, including definition of community standards, such as we're talking about today. So in parallel, a group of people were assembled to work on developing a workflow, building on the H2O2 paper that you had done, building on the work of Taranya and his group, the work of Burke and Dreyer and all these different groups. Not so much developing a new mechanism, but developing a workflow for the community continuous evolution and improvement of reaction sets. In general, the sort of workflow is the sort of thing that you would think of logically, but note, the different participants had different roles, some activities, choosing what quantities of interest, what features of data to test against, was an activity that had to involve the whole group of people. On the other hand, putting together an initial reaction set, my student and I put together an initial reaction set, and so on. Identifying sets, including uncertainties, crucial to this effort because, again, we know that there are uncertainties. Richard West has done some phenomenal work with codes that do consistency checks, not talking about truth, talking about consistency among different models and the parameters that are chosen, running models, building a response surface, a surrogate model. You'll hear about bound-to-bound data collaboration later, and of course reassessment of the data, because we do not believe data absolutely. We believe data is truth, but perhaps truth through a dark mirror, hard to see. Likewise, the models, we know that there are uncertainties there, but then we can optimize parameters within the bounds. So for this workshop, I want to speak very briefly at the close of my talk about the data storage format. Again, Nadja will present more about using Prime, but there are about 100,000 data files, not data points. There are some millions of data points, but data files, these are the catalogs of activities. So there are catalogs for reactions with multiple rate coefficient files for over 17,000 different reactions, and so on. There's shock tube data, flame, rapid compression machine, flow reactor. I think yesterday you heard some about the coal pyrolysis database that's built. There's even a team of Tibetan Buddhist scholars who are looking at Buddhist manuscripts using this tool to analyze the translations. So there's some very interesting and not obvious applications of this. But just in general, looking at a sweep of XML, but breaking it down a little bit, for a given experiment, for example, there's the intro information, including, I would note, a unique data identifier, and our next two talks are going to be talking about the need for data identifiers, because you can't search it effectively unless you have a unique identifier. The bibliographic information, the description of the apparatus, the description of the properties of the experiment, say the mixture of fuels, a hydrogen, oxygen, argon in this case, what mole fractions, or whatever other characteristics. It's built so that you can put in different features. It's extensible. And that's something we have to be very focused on with our data infrastructure. And then down at the bottom here, the data group itself. So in this case, it's T5 and the time to the steep pressure rise. Here's the temperature, here's the time. In microseconds, again, the infrastructure has to identify units. It has to identify all the pieces, including there has to be a copyright protection so that other people don't take and misuse the information. And also uncertainty. So in the different properties, different ways of reporting uncertainty, percentage uncertainty, a factor of uncertainty, an absolute number uncertainty, plus or minus. It's different for different things, but in many cases, we well-meaning experimentalists don't write down what the uncertainties are. To really compare against models, we need to know that. Similarly, if we look at data identifiers for use in the search, the infrastructure is allowed to search for, say, all papers by Davidson that have data in them, or all the data on set. In this case with Davidson, here's the file from the bibliographic entry. There's Dave Davidson. Again, you see the prime ID matches in there, the full details that you can go to. Of course, you can even save copies of the paper or copies of the equipment diagram or so on, the metadata that are important. And finally, this extensibility, I would point to the idea that you can put additional types of data, comments, but also, as I said, equipment diagrams, the calibration procedures, the calibration approach, the calibration parameters, and so on. So again, here's an example of that data item there. So again, the current plans that we've been working on with the team is to use Prime, and the activity is focused on maintaining first a stable version of Prime. There was a time when it was changing too frequently, but it needs to be accessible from different operating systems or computers, developing additional features and usability. Now there's a community team that's taken over managing it. As it turns out, a team of people developing software, not just one laboratory, and for that matter, accessed by remote server apps like Sarathi's CloudFlame code, video training that's available. The data warehouse itself is being taken over by Stuttgart, so it'll actually be European-based workshop. Again, Nadja will talk about that. And then finally, trying to shift from solely server-based calculations and server-based data, but to locally based data, particularly until you're ready to publish it, to share it broadly. You still want to be able to analyze it even before it is released, but also to run the codes. You cannot pump data from big turbulent flow calculations around the web. You have to ship the disk or the RAID array from one place to another on an airplane. So in summary, U.S. government agencies have sponsored a series of activities of development. The Combustion Institute is not sponsoring activity at present, but it still provides a platform results in our presentations. Both the government and the Institute want to see cultural change before they do anything. Both recognize the importance that it has to be international participation and has to be cyber secure. Frank Lack says just daily he has to turn down requests from people who are trying to hack into the Prime system there. And again, as I mentioned, the data warehouse in the cloud, but based in Stuttgart with the vision of a distributed data set. Thank you for your attention.